Continuing with section 4.5, we're currently in the middle of example 6, a problem involving Newton's law of cooling. Actually, we're applying this to a case where we have warming. We have a cooler that's sitting outside on a warm summer day, and it's slowly warming towards the air temperature. And we're trying to determine how long it will take for the temperature inside the cooler to warm to 50 degrees if it was initially at 30 degrees and the air temperature is 80 degrees. So at this point we determined that the constant governing the rate at which the cooler is warming is approximately 0.0074. So our model is, where can I write that here? It's, show it to you here. It's T of t equals 80 minus 50 e to the minus kt. So what we have at this point is T of t equals 80 minus 50 e to the minus 0.0074 t. So how long will it take for the temperature inside the cooler to warm to 50 degrees? What we're basically given here is given T of t equals 50 degrees. We want to solve for little t. How long means determine little t, the time required for the cooler to reach 50 degrees. Okay, so we need to solve an equation where T of t is 80 minus 50 e to the negative 0.0074 t. So we need to write that on the left-hand side here. 80 minus 50 e to the negative 0.0074 t, that's T of t, equals 50. Okay, now we're basically solving an exponential equation for little t. We need to isolate the exponential part. That would be this part right here. So what I'm going to do is I'm going to subtract 80 from both sides. Okay, so let me move that up here now. That would be, on the left I would just have negative 50 e to the negative 0.0074 t. On the right I would have 50 minus 80 is negative 30. If I divide both sides by negative 50, I obtain e to the negative 0.0074 t equals negative 30 over negative 50 is 3/5 or 0.6. Then to solve for t, as we've done many times before, we'll take the natural log of both sides. On the left, that's just going to give us what's in the exponent. On the right, the natural log of 0.6, which is a negative value, so t is going to be positive. So t would be the natural log of 0.6 divided by negative 0.0074. And to the nearest minute, it's about 69 minutes. Now, if we take a look at this problem, it says that during the first 30 minutes, it warms from 30 degrees to 40 degrees. That's a 10-degree increase. We want to know how long it will take the temperature to warm to another 10 degrees to 50 degrees Fahrenheit. From its initial temperature of 30 degrees, it's going to take 69 minutes according to the latest computation. In other words, it took 30 minutes to warm from 30 degrees to 40 degrees. It's going to take 39 minutes to warm from 40 degrees to 50 degrees. So you can see that the rate at which the cooler is warming is decreasing. It's warming, but at a slower and slower rate. It takes a longer amount of time to warm by the same amount that it warmed during the first 30 minutes. Our final example, example 7, is another logarithmic model. The number of years y from present time required for a city's population to reach p thousand can be predicted by the function y equals negative 500 plus 70 times natural log of p. So y is time in years, and p is the population of a city in thousands. Part A says, in how many years is the population predicted to reach 2 million? Now, for 2 million, we would want to let P be 2,000, because 2 million is 2,000 thousand. A million is 1,000 thousands. So P is measured in thousands. So we should use P equals 2,000 here, not 2 million. Okay, we have to be careful of little things like that. So in how many years, that would be solved for y. The model we're presented with, this logarithmic model, is already solved for y. So this should be a relatively straightforward computation. Y equals negative 500 plus 70 natural log of 2,000. And then that can all be entered directly on your calculator. To the nearest year, that would be 32 years. So according to this model, it will take 32 years for the population of the city to reach 2 million. Now part B says what population is predicted in 50 years. So in this case, we're given, instead of P, we're given Y. Y is 50. Here we now want to find the population P. Okay, so we're going to use the same model. We're going to replace y with 50. And on the right we have negative 500 plus 70 ln p. Okay, we need to try to solve for ln p first, so let's add 500 to both sides. That's going to give us 550 on the left, adding 500 to 50. And then 70 ln p on the right. We want to solve for ln p, so we need to divide both sides by 70. So ln p would be 550 divided by 70. I'm going to use a decimal value rounded to 3 decimal places for that. That's about 7.857. Okay, so what we have here is a logarithmic equation. We need to solve for what's inside the logarithm. As we did in the Richter scale magnitude example, we need to convert the logarithmic equation to exponential form. The easiest way to do that with a natural logarithm is simply exponentiate both sides of the equation to cancel the exponential and logarithmic expression and solve for p. So what that would give us is p equals e to the 7.857 power. So to compute the population, we have to evaluate this exponential expression. Recall that on your calculator that requires you to use second ln. Second ln will allow you to raise e to a particular exponent. What this gives us, and again this is a rounded to the nearest hundred, is 2600. But we have to keep in mind that this is 2600 in thousands of people, because p is measured in thousands as stated in the problem. So the population that we're actually talking about here is 2.6 million. That is 26,000 thousands is 2,600,000. So the population would be predicted to reach 2.6 million after 50 years. That concludes the notes for section 4.5.